Um, hmm. I've got kind of an interesting warm-up problem here for you in that. So far, you're the only one who's here. Uh, we'll bring everybody in on this as people no doubt will be arriving pretty soon. But this is an example of us using the kind of information that we're learning here in order to be able to understand our world a little bit more in depth. Here we just started. Hey, how you doing, Sierra? Hey. Um, and in fact, I'm wondering, I'm actually going to see if I can bring my laptop like right here so that I'd be working kind of at the same location. So if you could actually restrict, you could sit at one of these two tables. That would just be wonderful. I'm experimenting with whether or not this will make it so that you feel a little bit more comfortable with um, asking questions in class. I worked with my students earlier today, so who knows, maybe next time. If you could sit somewhere and you
Why do you have a slide up about Justice
yeah, but Justice Brett Kavanaugh. This is a chance for us to apply some of the stuff that we've been learning in probability class, not intending to be partisan here at all. But this is an example of some ways in which we can use probability information to try and shed some light on what's going on here. This is Brett Kavanaugh, who was nominated to the U.S. Supreme Court on July 9th, 2018, to fill the position vacated by Anthony Kennedy. Before his U.S. Senate confirmation proceedings began, there was a woman who came forward to accuse him of sexually assaulting her in the early 1980s. Three other women also accused Kavanaugh of sexual misconduct, one of whom later recanted her story. So he has a total of three women who have accused him of this. Okay. None of the accusations were corroborated by eyewitness testimony, and Kavanaugh denied all of them. So I can remember when this came out, and this is around the time of the Me Too movement, and so naturally there was a lot of support for the ladies who were coming forward here. I understand that. There were also a lot of concerns that were coming forward here about whether or not this person's being entrapped, or if this is a way in which a means by which someone can get sabotaged with false claims. And so let's actually put some data behind this a little bit. How often do false reports come out? Where somebody, usually a woman, gives an accusation of sexual assault, as it turns out, and those things turn out to be false here. A multi-site study of 8 U.S. communities, including over 2,000 cases of sexual assault, found a 7.1% rate of false reports. Okay, so 7.1% of the time. There were some other studies that gave some slightly lower percentages on that. I'm using the one with the highest percentage. Yeah.
Since this is a study from 2000 to 2003, don't you think this data is a little expired in terms of?
That's a good question. That's a reasonable question that we could ask here. Do we have some reason to think that false reporting might have changed just in the 20-year period? We could spend some time debating that. So that's a reasonable question to ask.
People are increasingly scumbags.
So you would make the case that there's reason to believe that this percent of false reports has increased.
Especially data like this.
Yeah.
Okay. When it comes to this type of data,
yeah,
what we were taught for Air Force is that you want to look about between a 5 and 1 year period for it to still be relevant.
Gotcha. Okay. Very good. I actually couldn't find anything that was more recent. So understood as far as I can do here. Yeah, right. There were 2 other studies, one from 2010 and one from 2006. They had lower values that were existing there. Okay. So here's the question. What's the probability that all 3 accusations are false? This is something that we've actually learned how to do last week. And so or on the other side of that, what's the probability that at least one of them is true? Okay, this is, true and false complementary events, that kind of thing. Okay. So how do we do this here? The probability that one of them is true, how do we figure that out? Let me see actually if I can pull my laptop over here just to make people thoroughly uncomfortable. I killed the speaker just to make people thoroughly awkward and uncomfortable. So put that right here.
For the data that we're doing, is there like a guess population or like when it came to that one uh that it did from 2009, was it like from a population of 2,000 and
They were spread out
59?
among a different set of U.S. cities. I don't remember which U.S. cities they were.
I know that had a certain number of how many people they asked if I remember.
2000.
2,000?
2000. Yeah. So if we take a look at this, and sorry, this isn't in your workbooks here. So let's just kind of talk through what this is here. The probability that one of them is false was 7.4%. Okay. So as a decimal, that's that. Okay. We could ask what's the probability that at least one of the accusations is true? That's a hard question to ask because, okay, what if the first one is true, but not the second one and not the third? It's easier for us to ask what's the probability that all three are false. And for that, if we make some assumptions, we can use the product rule on this when we multiply 0.074 three times, 0.074, 0.074. Yeah, Todd, do me a favor. If you could sit somewhere, you could even sit here if you want, but somewhere in these middle two tables here. Appreciate it. Okay, and what do we get when we multiply those three things together? We're going to get a tiny number multiplied by a tiny number multiplied by a tiny number. We should get a really tiny number. What do we get? Yeah, 0.000405. I'll say that 0.000. You know what? We've made this arrangement here that we're going to round it this way. So, okay. So the probability that all of them are false is this, which means the probability that at least one is true. That's the complement of that. So that's one minus this. And that would be 0.9996, which is 99.96%. They never did. Yeah. So this is a line of argument, not without some holes, which suggests that there's a 99.96% chance that Kavanaugh is guilty of at least one of those three sexual assaults that he's been accused of. Now, let me back up. Let's take a look at some of the assumptions that we're making here. I'm basically treating this like a binomial experiment. Okay. And there are four assumptions that you make when you are dealing with a binomial experiment. Number one, that it's a finite number of trials. Number two, that oh gosh, I'm having a brain fart now. That that the trials are independent of each other. And we could spend some time debating on whether or not these trials are truly independent of each other. And we could actually describe this a little bit more. A third assumption is that the probability doesn't change throughout the experiment. Rolling a die is rolling a die. Every single time the probability is the same. And so
is this a binomial experiment or is it not a binomial experiment? And does the degree to which it departs from a binomial experiment mean that it's completely invalid or maybe just partially invalid? There are those who have made the case that A, when someone has made an accusation, the chances of someone else making an accusation go up. In which case these trials are not independent and the probability does not stay the same going from one to the next. Okay, so that's one whole. The second objection that can be made to this is that the question has been raised as to whether or not this number applies. This kind of gets at what Noah was saying here. He was talking about whether or not it's increased in the past 20 years or so. We can also ask the question is whether or not what extent does this increase when you're dealing with a public figure? A person whose Twitter feed has 10 million followers versus 12.
Money.
Okay. Money and politics and all of those things, power, when you're dealing with a powerful person, there's the possibility of that chance of false reporting going up. Okay, so remember when I said that you get a little less judgmental when you're right. Plus, and there's actually a third point that you could make here. I'm not too wild about the precedent that this kind of sets here. If you have somebody who's been accused of 3 different accusations, well, somebody does this calculation. Well, he's 99% guilty. We don't even need to have a trial. So that's pretty bad. Okay, so this could be something that short circuits due process. So we still need to take a look at the details of the case here. So this is an important tool, but it's also important to understand the limitations of the tool. See what I'm saying? Yeah. Of course, with Bill Cosby, this came out. This was very, very painful to my generation because we were all like, this guy taught us how to read, and he taught us he was like America's dad, and he was like an example of a family man who was doting on his kids, and we loved him and stuff like that. He had slightly more people coming forward assess him. So yeah, if you take 0.074 and you multiply it 62 times, you get this astronomically small number.
What did he do?
Chances. His method of choice would be to roofie some drink, and the woman wakes up a few hours later in his car outside of his house, and he's like saying, "Well, get a bus ticket home." So
Did he kill them or just
he didn't kill them, but he sexually assaulted them quite a bit, and so yeah. Yeah, and he did eventually confess that these things were true. So yeah, that was hard. That would be like if you're for your generation, if the guy from Blue's Clues or something was accused of having a dungeon in his basement or something like that. It was like, wait a second, that can't work. So anyway, just this is a chance for. Remember when I said these are tools to apply to the real world here to combat, like I say, fake news, and to be able to take a look at things intelligently. So I hope that was helpful. Okay, probability distributions here. Okay, so a lot of this stuff here is going to be fairly straightforward. It's going to be a repeat of some of the probability discussions we had last chapter here. Chapters 4 and 5 are very quick, so we'll go through those pretty soon here. So we do have the test on chapter 3 this Thursday. Chapter 4 and 5 usually has a test together, because there's not a whole lot of additional content there between the two of them here. But probability distributions here, okay. We're going to define this new thing called a random variable. And what is a random variable? It's a variable that has some randomness in it. How's that for a, kind of a lame definition there? But it's a variable whose value is somewhat, defined by some random events that are happening in a given moment. So a good way to describe random variables is through things like probability distributions. We'll describe what those things look like here. Okay. Here are some examples of random variables. Boy, if you're an insurance company, you're dealing with random variables all the time. Assigns probabilities to the number of vehicles a family owns, the number of kids that are in a household. That's those kinds of things. A saleswoman computes the probability that she will make 0, 1, 2, or 3 or more sales in a single day. That's the hard part about selling cars. My wife used to sell cars. You sort of making nothing, 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 and then all of a sudden you make $10,000 in one day, and you have to hang on to that for the next famine that you're going to have there. So, um, a band computes probabilities for giving 0, 1, 2, 3, or 4 or more performances each week. Okay, so 60% of the time this happens, 40% of the time this happens, 30% of the time this happens, and so on. So, like I said, a random variable is a variable whose values are determined by chance. What determines whether or not I have, 3 people buying cars today, or just one person, or nobody? Well, we could investigate that and come up with some very complex reasons, but it's probably just best to treat it as this random thing. Okay, and if you recall, these are quantitative, and we've beforehand divided quantitative variables into 2 parts, 2 types, discrete and continuous. So tell me which one you think this is here. Number of joggers in downtown Greeley. Discrete or continuous? Discrete, you're right. You can't have a half a jogger. Weights of vegetables at a farmer's market. Continuous. You can have a half a pound of something, or an eighth, or a tenth. Temperatures around the UNC campus, given in whole degrees.
Maybe discrete.
It's just,
Continuous.
I could argue one way or the other on that. Okay, let's assume that, we're slicing them up into tenths of a degree or something like that. Number of phone calls received after a Super Bowl ad plays.
Discrete.
Discrete. Generally, if you see the words number of in the beginning, that's definitely discrete there. All right, so let's take a look at an activity that I have here. It's listed in your workbooks here. I have to pull this up, separate Word document here. And let's just see if we can ascertain how this works here with this. Let's see how this is going to work here with this. If I flip a coin, what are my 2 possibilities here? Hey, could you do me a favor? And maybe sit at one of these 2 tables here. Thanks, man. Appreciate it. In the first flip, I've got 2 possibilities, heads or tails. In my second flip, heads, tails, right? And also if I flip tails the previous time, I could either have heads or tails in my second flip. If this event happens, how many heads did I have? 2. If this event happens, how many? 1. If this event happens, 1. And if this happens, 0. Heads. Those are both tails. Yeah. So if I flip a coin twice, the probability that I get no heads is 1 in what?
1 and 2.
Well, how many possibilities are there? 4? And how many of them,
Oh, that's right.
how many of those possibilities do I get? Ooh, you're making this way too hard here. How many possibilities are there? 4. And in how many of them do I get 0 heads? 1. 0 on the end. Yeah. The probability of getting no heads. So it's 1 in 4 here.
So you're flipping 2.
We are. And in the same vein, what's the probability of getting 2 heads? Also 1/4. 1 out of 4. How many instances do we have where we get one head? Two out of four, which can reduce to 1/2. So if you are flipping two coins, you have a 50-50 chance that one of them is going to show up as a head, exactly one. You have a 50-50 chance of getting heads, tails. So this right here is an example of a probability distribution. You list all the things that can happen, and you list the probability of each one of those things happening. Okay, so let's do this again for 3 flips of a coin. Heads, tails, that's the first flip. And you can almost think of this as a tree diagram. Coming off of this one here, we could get heads for the second flip or tails for the second flip, heads for the second flip, tails for the second flip. And then for the third flip, each one of these gets divided into heads or, gets divided into heads or tails, heads or tails, heads or tails, heads or tails. So how many different outcomes do we have for each individual flip? But in all of these possibilities here, how many different possible outcomes do I have? Is it 12? I'm looking down here and I'm seeing basically a number of boxes down here. How many boxes do we have? 8. So we have 8 possible outcomes here. Okay. If we were to flip 4 coins, what do you think we'd have? 16. We'd have to double it again. Yeah. So we have 8 possible outcomes here. And since we treat this as heads and tails being exactly half and half probability here, we could figure out, what the probability is of each one of these things happening. For this case here, how many heads did we get? 3. So all 3 of them came out as heads. How about this possibility? Heads, heads, tails. 2. Heads, tails, heads. 2. Heads, tails, tails. 1. Tails, heads, heads. 2. Tails, heads, tails. 1. Tails, tails, heads. 1. Tails, tails, tails. 0. Okay, so what is the probability if you're flipping 3 coins here that you're going to get no heads? 1 in 8. And in the like vein, what's the probability of getting 3 heads? Also 1/8, yeah. What's the probability of getting 2 heads? 3/8. And 2 heads? 3/8. So we have another probability distribution there. By the way, what should all these probabilities add up to? 1. And you see that here again. 1/8 plus 3/8 plus is 4/8 plus another 3/8 is 7/8 plus another 1/8 is 8/8, which is 1. Yeah. Let's do the same thing for rolling a single die. The probability of each one of these. What's the probability of rolling a 1? 1/6. And a 2, 1/6, 1/6. And again, what do all these things add up to? 1. Yep. 6/6 or 1. Yep. Now let's see if what happens when we roll 2 dice together here and see what the total is of those 2 dice. Okay, so this gets to be a little challenging here. So you got a bunch of different numbers here. What's the total here of a 1 and a 1? 1 plus 1?
2.
2? 3. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6. 1 plus 6 is 7. Okay, so if the first die is a 1, your total might be 2, 3, 4, 5, 6, or 7. The second one is a 2. 2 and 1 would be 3. And then 4, 5, 6, 7, and 8. If the first die is a 3, then your total might be 4, 5, 6, 7, 8, 9. If it's a 4, possibilities are 5, 6, 7, 8, 9, and 10. If it's a 5, the possibilities are 6, 7, 8, 9, 10, 11. And lastly, if it's a 6, the possibilities are 7, 8, 9, 10, 11, and 12. How many total outcome possibilities are there?
36.
36. This is 36 numbers that we've got here. 36 possibilities. So what is the probability that you're going to roll 2? There's only one possibility there out of 36. So yeah, there's only one way to roll snake eyes, as they call it. And in the same way, what's the probability of getting a 12? Also 1 out of 36. Now, if we take a look at rolling a 3, how many possibilities are there? There's 2 of them, here and here. So that would be 2 out of 36. And in the same way, what's the probability of rolling an 11? Also 2 out of 36. You can see them here. How about rolling a 4? 3 out of 36. How about rolling a 5? 4 out of 36. How about rolling a 6? 5. How about rolling a 7? 6. 1, 2, 3, 4, 5, 6. How about rolling an 8? Now we're going down again. 5. Interesting.
Is it
Okay.
4
For,
weeks? Or is it 5?
I think it's 5. Because I'm seeing, yeah, 1, 2, 3, 4.
Oh.
So, so if I were to plot this, what would it look like? What would those bars look like? Oh, sorry. Duh. Come on, with red. Look like a pyramid. Yeah. With the apex where? 7. So now you know why rolling a 7 in a lot of dice games is kind of significant. 7 is the most likely sum that you can get of 2 dice. You have a 1 in 6 chance, 6 out of 36, a 1 in 6 chance of getting a sum of 7 when you roll 2 dice. Yes. Yeah, these were examples of totals. So yeah, in this case, we rolled a 1 and a 1, so the total was 2. If we rolled a 1 and then a 2, the total was 3, and so on. Yeah. So you could, and we were asking what this would look like. It would look like that, except it would be bars. It's always been my favorite ringtone. Okay.
Hold on, would you mind scrolling back up?
Yeah.
Thank you, sir.
Yeah. Now, we could have some fun with this a little bit more here. How many of you have played Dungeons and Dragons? One person. Oh, one person? 2 people. Okay, 2. Yeah, that's right. One of the things that you can do in Dungeons and Dragons when you're rolling dice sometimes is you can roll with advantage. Sometimes your character is able to do that. When you're rolling with advantage, what happens? What's that? No, those are bonus points. When you're rolling with advantage, you get to roll the die twice and choose the higher of the 2 rolls that you got there. So you have 2 chances to get something high. And I can show you here. Come on, get out the way. Yeah, go ahead. Yeah,
It's
it's a lot of stuff going on. sorry, I thought this was gonna show up here pretty quickly. But I can tell you that what this ends up looking like it ends up basically looking like this. Instead of being a pyramid, it kind of, makes it so you have a much higher probability of getting something that is high. And if you're rolling with disadvantage, where you have to take the lower of two rolls of a d20, it looks like that. So you have a much higher probability of getting something low than you do of getting something high if you're rolling with disadvantage. So anyway, that's what those things look like there. All right, so let's come back here to our workbooks, or at least the portion of the workbook described here. Number of heads for two flips of a coin. We saw actually a pyramid shape here as well. No heads, one head, two heads. Most common possibilities to get one head out of the two. For three flips of a coin, we kind of saw this same symmetric pattern here, like this. And what's interesting is that, yeah, if we're just rolling one single die, we get a nice uniform distribution like this. But if we add two dice together, we get our pyramid shape there like that. Interestingly enough, guess what it looks like when you are rolling three dice? It starts to look a little different. It starts to get flattened out up here, and it starts to look more and more like a bell shape. So actually, that's where normal distribution comes from. Imagine rolling an incredibly large number of dice, theoretically an infinite number of dice, a bunch of times, and adding them up each time. What are you going to get? It's going to be something that distributes looking something like this. That's actually what it is. Okay. Uh, all right, so let's create a probability distribution for some real life things here. A convenience store sells AA batteries in 2 per package, 4 per package, 6 per package, and 8 per package. The store sells 5 2-packs, 10 4-packs, 8 6-packs, and 2 8-packs over the weekend. Construct a probability distribution and draw a graph for this. Well, okay. So what are the possibilities for selling AA batteries here?
2, 4, 6, 8.
Yeah, 2-pack, 4-pack, 6-pack, and 8-pack. Oops. And what's the probability here of getting a 2-pack?
2.
How many packs were sold overall? Yeah, it's a 25. Let's see, it's 5 plus 10 is 15. Oh, 8 and 2 is another 10. So 10 plus 5, 25. And how many of those were 2-packs? So 5 out of 25. How about 4-packs? 10 out of 25. Okay. How about 6-packs? 8 out of 25. And 8-packs, that's 225. Okay, and as a decimal, this is going to be 0.2. This is going to be 0.4. This is going to be 0.32. And this is going to be 0.08. So this is what our probability distribution table might look like here. Okay, and can we plot this as a bar graph?
Yeah.
Yep. So we've got 2-pack here, 4-pack, 6-pack, 8-pack. Consumer behavior. Or purchasing AA batteries. Okay, so how high does this thing get? Gets up to 0.4. Okay, so 2, 0.1, 0.3. 2-pack is 0.2. 4-pack is 0.4. 6-pack is 0.32. That's going to be about here, I guess. And 8-pack is 0.08. Okay. So next customer coming in wanting to buy AA batteries, you're seeing a probability distribution here, an empirically derived probability distribution on what the behavior might be. It's a little neater right there. Okay. Which of these are legit probability distributions and which ones are not? Well, let's focus on one of them. So somebody make a comment about just one of them. D is not. Why not? Doesn't add up to one. Also, there's another problem with D.
Can't have a negative probability.
Can't have a negative probability. Okay, so this is a no. All right, what's another observation to make here?
It isn't because it adds up to more than one.
That's right. Must add to 1. So this one's a no as well.
B isn't because there's a 50% chance to get a red bag.
There's a, sorry?
There isn't a 50% chance to get a red bag.
Well, I'm looking at actually, it's not a question of whether or not it's realistic. It's a question of whether or not it's valid. But you're right to be focusing on B. What's the problem with B?
Too much, just
Yeah, we're repeating the same possibility here more than once. So shouldn't have a repeat like that. So no repeats. So that's also a no. This one's okay. No such issues there. All right. Making sense? Okay. Okay. So that's a very, very short section there. We'll find the assignment to be pretty straightforward for that one there, hopefully. But here are some things that we can actually do with these probability distributions. We can start to talk about what's the average of these probability distributions, and I'll let you know it's a different procedure than what your spreadsheet does. It's a common pitfall people get into. I'll find the average of this. Oh, just spreadsheet. No, it's a different set of thing here because we're actually talking about something slightly different when we say the average. See if I can come up with a quick example. Let's say there are 20 rooms in this building here. I think there are kids that are walking around here a little bit. It's a college. What is it? I'm trying to remember. It's a summer camp, early college, something like that. Let's say that all the rooms are unlocked and the kids are encouraged to explore. And there's 20 kids. On the average, how many kids should you find in each room? 1, since there are 20 kids in 20 rooms. That's what it means to find the average of a probability distribution. Okay, but in reality, you might walk into a room and find none. You might walk into a room and find 7. You might walk into a room and find 4 or 2 or 1. But on the average, You should find one per room. Okay, so that's the idea here. Here's the same kind of problem. I'm rolling a die 30 times. Remember, the probability is 1/6 for each one of these things. How many times would you expect to roll each of the following? A 1. How many ones would you expect to have if you're rolling 30 dice? 5. Yeah. Now, how'd you get 5? Yeah. Yeah. And in the same like vein, how many 2s would you expect? Also 5, 5, 5, 5, 5. And so we could say that he's getting this. The number of trials that we have is n here. The probability here of getting a 1 is 1/6. And you're multiplying that by the number of trials, aren't you? And you're getting 30 divided by 6, which is 5. What would be the mean value of all the rolls added together? What would be the average of all the rolls? Because I've got 5 1s, 5 2s, 5 3s, 5 4s, 5 5s, and 5 6s. I have to find the average of all those dice. So interesting. You're saying 3. Oh, 30. Okay. There's 30 rolls here. It's going to be some number between 1 and 6, right? Yeah, let's think about this a little bit more here. Yeah. I'm going to have 5 1s. How do I find just a simple unweighted average? Add them all up and divide by 30. Okay, so I have 5 1s. What do those add up to? 5. 5 1s. 1 1 1 1 1. What do those add up to? 5. Okay, good. We've all been there. 5 2s. What do those add up to? 10. Good. 5 3s. 15, 20, 25, and 30. Okay. So let's add up all of these things and divide by what now? How many dice are there? How many dice? 30 dice. Okay, good. This is 30, 55, 75, 90, 100, 105. I think I got that right. So our average value here should be that. Actually, should represent it that way. See, 30 into 105. What is that? Somebody with a calculator. 3.5. Interesting. So the average value of all the dice being rolled should be 3.5. Look at where that is in this distribution here. Does that make sense? Yeah, right in the center. Yeah. Makes a lot of sense. Yeah. So you can see that's the math that we had to go through here. And so this is actually something that you can take a look at various games that you can play either at Vegas or at the corner drugstore or it's a drugstore. The 1980s called, John, they want to have their reference back. Gas station or something if you're buying a lottery ticket or playing this kind of lottery game or that kind of lottery game. One of the ways in which you can evaluate the relative amount of risk that you're taking with each one of these and which one to take is what's the expected value of a $1 bet in each one of these things. In other words, if I play this game over and 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 over again, sometimes I'll win, sometimes I'll lose, but on the average, what's going to happen? Okay, so we'll do some of that. And it's all about constructing statistics on probability distributions here. Okay, so just watch the algebra here just a little bit. Don't think you have to know how to do this. This is just, if you're interested, this is the calculation that we had to go through here. And another way of saying that is we can divide them up into all these fractions here that were like this. You can pull out the ones in front here and simplify all those fractions. And what we're seeing here is the value of the dice times its probability. The value times its probability. The value times its probability. And then we're adding all those things up. So values and probabilities means that if we take every item in our probability distribution and take the value times its probability, multiply those things together, and then add them up, we get the expected value. Okay, so this is a nice, easy formula to remember with this. This is just another way of saying it here. This expected value is the same thing as the mean. We just have a different way of saying it because it means something a little different. Like what would you find on the average of all the, playing this a bunch of different times here. So expected value of X, it's another way in which we say this. And so calculate the average value of the number of heads when you're flipping a coin 3 times. Okay, well, there are 4 different possibilities here with 4 different probabilities. The first event is to get 0 heads, right? That has a probability of 1/8. The second one is that you get 1 head. That has a probability of 3/8. Third probability is you get 2 heads. That has a probability of 3/8. And then lastly, you have this probability on the end over here of 3 heads, which has a probability of 1/8. Okay, so let's multiply these things together here. 0 times 1/8 is just that. 1 times 3/8, well, that's still 3/8. 2 times 3/8 is 6/8. 3 times 1/8 is 3/8. Let's add those up, and we get 12/8, which can reduce to 3.5 or 1.5. Look at where that resides. And if somebody were to ask you, I'm flipping 3 coins, on the average, how many heads would I expect to have? Well, half of 3, 1.5. This is where we get into, the average American household has 2.5 kids in it, like we can slice a child and, something like that. I mean, that doesn't make any sense for a particular household. For an average, it makes a lot of sense. Okay, so just introducing you to this particular kind of math problem here with this. Okay, what's the average value of the total of 2 dice? Okay, here, the only difference between here and here is I've simplified the fractions a little bit. I think that's actually makes it harder, so we'll deal with these values up here. So this is X, this is P of X, and so I want to have a third row here, a third row here that is X times P of X. And so let's just go down the line here for each one of these. 2 times 1/36 is 2/36. Okay. 3 times 2/36, 6/36. Good. 4/1 times 3/36, 12/36. Good. 5/1 times 4/36. And we're just multiplying tops, multiplying bottoms. 20 out of 36. And this is going to be 30 out of 36. Good. This is going to be 7 times 6, 42. Good. And then 8 times 5, 40. 9 times 4, 36. 10 times 3, 30. 11 times 2, 22. And lastly, 12 times 1. There we go. And we just have to add all these things up here. And here, I'll just let the PowerPoint take over here with this. So when I add up all those fractions, I'm going to get, interesting. Does that make sense? Again, right in the center of a symmetric distribution. It really is, in this case, the same as the median. The fact, so it's just like when we were dealing with histograms, the fact that it's a symmetric distribution means that the mean and the median are in the same place. Yeah. Okay. The roulette table. Just so you know what the roulette table looks like. How many of you have seen this and know what this is? If you watched a James Bond movie, it's kind of a, so I have my martini and what they do is they have this thing that gets spun. It's got a bunch of different slots where little marbles can roll into. And so they, send a marble, rotating around this thing. It's eventually going to fall into one of those slots. What are the slots? Well, they're numbered 1 through 36. And there's also two other slots. There's a 0 and a double 0. Okay, and so you basically place a bet on one of the numbers. If it lands on that, you win. If it doesn't land on that, you lose. You could either bet a single number, or you could say it's going to land on one of the red squares or one of the black squares, or it's going to land somewhere between 1 and 12, or 13 and 24, or 25 and 36. That kind of thing. Okay, so you can make those kinds of bets here. So it's essentially a way of stating a bet, and then they place your bets. Okay, this person's betting on red. This person's betting this much on it being odd. This person's betting on this much on it being 1 to 18. So they eventually, collect the chips and give back here. So you're placing $1 bets on a single number. Since there are 38 slots, the probability of winning is 1 out of 38. Do we agree? Yeah. When you win, you get 35 bucks, since the house odds are 35 to 1. Interesting. It's a little different. Little less than what you might expect. Otherwise, you simply lose the dollar. Calculate the average profit of playing the game. Well, there are two possibilities. Either I'm going to win or I'm going to lose. All right. If I win, I get 35 bucks, right? If I lose a buck. And what are the chances that I'm going to lose? Well, these two things are complements of each other, aren't they? Okay, so instead of 1/38, this will be the remaining 37/38. And so what is the overall expected value of playing this game? I get this.
Would you say it kind of looks like
Well, you already know that you're more likely to lose than you are to win. But you also gain more when you win than you lose when you lose. So the question is, what's really happening? What this says is that if I play this game a million kajillion times over and over and over again, on the average, what's happening to me every single time I play this game?
So,
I'm losing how much?
or
5 cents. Yeah, 5.3 cents. Okay, so that's the risk that is going on here. Okay. And by the way, these are always negative, which is why when you go into Vegas, everything looks so bright and shiny, and lots of lots of heavy lights everywhere, and they're wining and dining you. Okay, it's because you're dealing with large financial entities that are not dealing with the winnings on a given day or a given weekend. They're dealing with what's happening overall with a million people playing. And when a million people are playing, on the average, they're earning 5 cents for every game that gets played. So they have the privilege of playing the long game, so to speak. Okay. So let's do the same roulette table. You're placing 10 bets on red. Okay, we've got a lot of red slots there. Of the 38 slots, 18 are red, and the house odds are 1 to 1. So winning results in you getting your $10 back plus another 10 bucks. So let's calculate the average profit of each game here. Either I win or I lose. If I win, how much do I get? 10 bucks. If I lose, what happens to me? I lose 10 bucks. What is the probability I'm going to win? 18/38. Which means these two things have to add up to 1. What's my probability of losing? 20. Good. 20 out of 38. So if I add these things together, 18 plus 20, There you go. So I have a slightly larger chance of losing, which is why the house always wins. All right. In particular, it's these strategically placed 0 and 00 things that throws the probability off very slightly. So they win in the long game here. Okay, so this is X, this is P of X. I have to create X P of X. Let's multiply these things together. I get 180 out of 30 out of 38. That's positive. And if I multiply these things together, I get 200 out of 38. So let's add these things together. And I get my expected value of this, which is also the mean of the probability distribution. And that gives me, it looks like negative 20/38. What is that? Can somebody give me what that is as a fraction? As a decimal, rather, sorry. 20 divided by 38. What's that? 0.52, did you say? 0.53. So what's happening on average when I play this game, the way I've set it up? I lose 50 cents every single time I play. Okay. By analyzing her sales records, a saleswoman has found that her weekly commissions have the probabilities in the chart shown here. Find and interpret her expected commission. So if she's getting a commission of 0, 5% of the time, a commission of $100, 15% of the time, a commission of $200, 25% of the time, and so on, what's her average commission that she's making on a regular basis so that she can budget? Well, this is X. This is P of X. Have at it. Talk to each other, help each other out. If you're stuck, take a look at the previous problem. Should I answer that? Just very much, if this feels a little deja vu-ish, this is the same procedure that we went through when we calculated a weighted average. except the weights now are probabilities. Okay, so let me see if I can get these rows of values here. What's the first one going to be here? 0. Yeah, these two multiplied, one of them 0. How about this next one? 15, good. Then 50, good. Then 135, yes. And then lastly, 40. Okay, so you found out all your XPXs. What's the sum of those things? 240. Okay, statisticians, interpret that for me. Expected commission each week. Yeah. So that's on the average what she's making each week. It's probably what you could use to budget on, you know. Okay. So you can see that as well. It's a little neater. Okay. 1,000 tickets are sold at $1 each for winning a smart television valued at $750. What's the expected value of the gain if you purchase one ticket? Yeah, again, if you lose, how much do you lose? $1. Okay. And if you win, how much do you win? How much do you gain in dollar value? Good, 749. You'd say 750, but you had to pay $1 for it. So your net increase there was 749, wasn't it? Yeah. Okay. What's your probability of winning? How many tickets were sold? 1 in 1,000, which means your probability of, oh, I'm sorry. This should be 1 in 1,000, shouldn't it? Which means that this here is what? 999. Okay. We've got our probabilities here for each one of these events here. So on the average, what are we gaining here every single time we invest in this? See, this will be 749 1,000ths minus 999 1,000ths. And that's going to be minus 250 over 1,000. Which is interesting. Does that make sense? So, yeah. Because from the standpoint of the person who's doing the raffle, they had to spend they brought in $1,000, but they also had to buy what? They had to buy a $750 television. So what's the net that they're getting out of this? 250. So on the average, for the total amount that they're getting in this fundraiser here, whatever they're doing, is $250, which divided among 1,000 people means they're getting on the average a quarter from each person. So you can see it that way as well. Yeah. Okay. Okay. 10 cards are selected from a deck of Uno cards. There are 2 cards numbered 0, 1 card numbered 2, 3 cards numbered 4, 2 cards numbered 8, and 2 cards numbered 9. If the cards are mixed up and 1 card is selected at random, find the expected value of the card. On the average, what's going to be the value of the card that you draw here? Well, kind of feels like they're describing a probability distribution, aren't they? What are the different possibilities here. Yeah, Sally. What's going on with this problem? Describe it in your own words. It's oftentimes the hardest part, isn't it? Yeah, I got you. But yeah, take a deep breath. Tell me what you think here.
Do we have 3 cards?
We have 10 cards total. Yeah,
And there are 2 cards on number 0
yeah.
and 1 card number 2. 3
Okay.
cards number 4. And then 2 cards number 8 and then 2 cards number 9.
So I'm seeing events and probabilities,
Mhm.
right? So what's the first event that they described here? But the number that you draw would be what?
2.
The number that, but what's the number you draw with each one of those 2 cards? 0. So that's one possibility. What's the probability of that happening? 2 out of 10. Yeah. What's another possibility here? 1 card. What's that probability? Also 2 out of 10. Okay. What's the next one? Careful. Math brain turned off. So we had numbered 0. Yeah. Number 2. Do we have any cards numbered 3?
4.
Yeah, the next number is 4. Oh, number 2. That should be, sorry. Oh my gosh. I got that reversed, didn't I? 2 cards numbered 0. 1 card numbered 2. All right, my apologies. So the next possibility is that you're going to pull out a card that has a 4 on it. And what's that probability? 3 out of 10. Good. And then the next one is 8 with a probability of 2 out of 10. Okay. And lastly, 9. And that has a good 2 out of 10 here. Let's confirm that all these add up to 1. 2, 4, 6 plus 4 is 10. So 10/10. That works. Okay. So we have a good solid probability table here. Okay, so how do I find the average of all the possible values here? The next card that I pull out of the deck, or the first card I pull out, got to find this strange thing. Let's first of all find what this strange thing is here. What's this first one? 0. 2/10, good. 12/10, good. 16/10, good. And 18/10, good. Now I just have to add those up.
48.
Good. 48/10, which as a decimal is just 4.8. Okay, so statisticians, interpret that for me. No, no.
The expected value is 4.8, but
The expected value, so how would you say that to a friend?
you're likely to draw 4.
No, it's not dollars. Likely to draw 4. If you were putting down, if you were to do this a bunch of different times, create that same deck and put down a card. Sometimes you'd get a 9, sometimes you'd get a 0, sometimes you'd get a 4, so on. But on the average, what would be the value of this card it's drawn? 4.8, yes. Okay, so yeah, if you go through this process, thank you. If you go through this process a bunch of times, on the average, the value of the card that you draw from this deck of 10 cards would be this. Okay. Okay. So, see how nice that looks? Tinseltown, well, not a Tinseltown, that's Hollywood, but this is there's a reason why the electric bill for this this part of the United States is probably sky high here. The house always wins. Why does the house always win? What is the sign that you see in front of all of these games here? It is a minus sign. So in every instance, no matter how you do in any given moment, you might clean out the house one night, but on the average, the house always wins. So which one of these, by the way, is the most risky? State lottery, yeah. So on the average, you're losing 48 cents there. On what's the least? Haven't heard the right answer. Yeah, the tie between Baccarat and craps. I actually don't know what Baccarat is, but yeah, 1.5 cents that you're losing each time you play those, versus 6 cents, 10 cents, 19 cents.
Or you're gaining 10 cents on blackjack. If you're actually good at that.
If you're actually good at the game. Oh yeah, gaining 10, right, right. And in fact, this is there's actually a movie that was created that described how some people, came up with some strategies so that they would win more often. They could change this expected value. I think the movie is called 21, came out about 10, 15 years ago. And it's actually a true story of an MIT professor that just helped them come up with a bunch of things. And they were going in team. Basically, what they do is they go in teams, and one person will just play with very, very low stakes, investing very little money, that sort of stuff. But they're counting the cards to see whether or not we're getting to a place where the dealer is about to draw some very, very, very favorable cards on the average. We haven't seen these in a while, so the likelihood is higher. When that happens, they give some secret signal, that brings over another person to come in and just play really quickly, and they're the ones that are going to play. They're going to bet a lot of money, and oh wow, they win, and then they go away. So that's the approach that they did there. And so yeah, they're doing this and they're winning, and then all of a sudden, large burly people take them back out. We think you're counting cards. Technically, that's not illegal. It's just if they have monitors everywhere in these things where they're taking a look at you, trying to see, if you're doing anything like this, and getting too smart for that. So yeah, that's right, exactly. So here's the kind of thing you see on TV all the time. It deals with something, it actually gets into something called decision theory. You're on a game show on TV. There are briefcases on the stage. You get to choose one. One briefcase contains $1, one has $100, and one has $10,000. If you choose the fourth briefcase, you lose the $8,000 that you've already won. Dun dun dun. Okay, so the lights are dimming down, and we'll give you 50 commercials here before we find out what they do here tonight. We all know how reality TV shows work. Also, you can choose to not choose a briefcase and simply keep your $8,000. Calculate the expected value, interpret it, and use decision theory to determine if you should choose a briefcase or not. Okay. So let's take a look at how things look if we choose to choose a briefcase here. Okay, so what are the possibilities here? If I choose a briefcase.
Plus one.
Plus one, yeah.
Plus 100.
Plus 100.
Plus 10K.
Plus 10K. And then what's the fourth option? I lose 8K. Yeah. And what are the probabilities of each one of these things happening?
1 in 4.
1 in 4. Okay, so let's see if on the average, if you were given this situation a gazillion times, what would happen on the average here? A quarter of $1 is a quarter. A quarter of $100 is 25 bucks. A quarter of 10K is 2.5K. And a quarter of negative 8K is negative 2K. Let's add all those things up. These two, this will wipe out this, leaving behind $500 plus 25 plus 25. So hmm. So decision theory gives you an answer here. What's the answer? Did you choose to risk this or not choose to risk this? On the average, what would happen if you were given this situation a gazillion times? What would happen on the average?
Oh, I didn't know.
Well, you're just stretch. That's right. So what would happen on the average if you did this a bunch of times? Is that number positive or negative? It's positive. You'd win 525 bucks and 25 cents each time you did this. So decision theory says make the gamble. Yeah. Well, make the, your chances of winning are slightly bigger than your chances of losing. So this enables you to actually, quite honestly, the way that you play games of chance, at least I do, is this takes all the emotion out of it. It becomes a mathematical calculation. So you can play the game calmly, so to speak. Takes all the stress out of it.
Just wondering what you have to pay for it, like invest into it, right?
Yeah,
You know, if it's worth.
that's right. Well, remember, this is $8,000 you've already won, and so I mean, yeah, it's your chance of. I mean, it's not like you're mortgaging your house to play this game. Okay, so decision theory says play the risk. The expected value of not choosing a briefcase is 0. The expected value of choosing a briefcase is this. So, okay. Here's another strategy that comes up here. I haven't tried this, but it seems reasonable. The martingale strategy is a gambling strategy in which the gambler doubles his bet after each loss. For example, a person and plays this until they win. For example, a person using the strategy in roulette betting on black numbers might lose 3 times before winning. This strategy would still result in a net gain. So, you bet $1, you lose. Okay, you've lost $1. So now in your round 2, you're going to double this bet to $2. Oh, you still lose. Okay, still double it each time, $4. And eventually you get to a place where you win. But when you win, you pay back all of this stuff that was here, and you still have a little bit left over. So it guarantees, assuming that you will eventually win, you will eventually, yeah, you will always walk away with a net positive from that. A financial advisor suggests that his clients select one of 2 types of bonds in which to invest $5,000. Bond X pays a return of 4%, but has a default rate of 2%. What does default mean?
Who's that?
No. Now, what does it mean to default on a student loan?
That you don't pay back.
You don't pay it, you fail to pay it back, basically. So, and your credit rating goes up the toilet if that happens. But yeah, a default is where the investor loses his money because it's not paid back, right? Okay, um, so for bond X here, there are 2 possibilities here. One is that the investor loses her money, and the other is that the investor does not lose her money and gets a return on it. Okay, so if the default happens, how much is lost here if the default happens? You lose $5,000. And what's the probability of that happening? 2%. Okay. If you don't lose it, you gain what? Whatever 4% of $5,000 is. That's actually 200. What's the probability of that happening? What's that?
No, she said 4%.
Not 4%. 98%. It's the remaining 98% here. Since these things, I mean, either it's going to default or it's not. Those things have to add up to 100%. Okay, do the same thing here with bond Y. See what you get here. If it defaults, what happens to your bank account? They're so cute. Got their little backpacks.
There you go.
Okay. What happens if it defaults? Lose 5,000. Okay. And what's the probability of that happening? 2.5%, right? 2.5%. Which-
That's the return.
Oh, you're right. My bad. 1%, sorry. Yeah, default rate of 1%, which means the probability it's not going to default is 99%. Yeah, the remaining 99%. And let's see, if it doesn't default, I'll get 2.5% of $5,000, which is $125. Okay, so take a look at this one here. Which one's riskier? Which one has a higher chance of you losing your money? Bond X. But which one has you standing to gain more money if it doesn't default? Bond X. That's oftentimes the case. The ones that have the higher returns also have the highest probability of defaulting. If you are, and you're at the age right now where you can have a lot of fun investing in things that are, that have high returns, like 14% returns, but there's a 20% chance you might lose everything. So if you invest in various things here. So for me, I have to be a little more conservative in my stage of life. But what we can do is we can game theory this out, game decision theory this out.
What about invest in the military industrial complex?
There you go. Sound just like Eisenhower.
He hated them.
He was the first one to make a speech about that. 98% of 200, so 200 times 0.98 is 196. And that's positive. And 5,000 times 2%, that's going to be negative 100. Okay, so the expected value here, or the mean of this probability distribution, is 96 bucks. Okay. Let's do the same thing over here. 1% of negative $5,000, that's negative 50. 99% of $125 is 123.75. Is that right?
123.
There we go. So that's a plus. And if we subtract or add these things together, these things add up to $73.75. So according to decision theory, is the extra rate of return for bond X worth the risk? Yeah. And again, this allows you to play the stock market without emotion, without panicking, and without euphoria. You're just, going by the numbers, and this is how we do it. So this allows you to, be a little bit more, what's the word? Systematic about it. Okay. All right. We've calculated the mean of these probability distributions. Guess what we can also do? We can calculate the variance and the standard deviations of these probability distributions as well. Okay, and this is the formula for doing this here. Okay, and so you can see, let's do this just for rolling a single die. We already know what we're going to get for an average here because the average value we already found was 3.5 when you roll a single die here. So let's see, x times p of x, what's this? 1/6. This is 2/6. This is 3. This is 4. This is 5. And this is 6. If we add those together, 6 plus 5 is 11, plus 4 is 15, plus 3 is 18. This is 20. It's 21/6, which is 3 3/6, or 3.5. Okay, we actually found that out a few slides ago. Let's take the x now and let's square it. 1 squared is 1. 2 squared is, you're ahead of me. 4. 3 squared is, ooh, talk to me. 9. 4 times 4, 16. 5 times 5, 25. And 6 squared is 36. All right. So now let's multiply these x squareds times the p of x here. So this times this. So 1/6. What's this one? 4/6. This one? 9/6. 16/6. 5/6. And 36/6. Okay, if we add these things together, somebody help me out here. So it's 5, that's 30, 20, 55, is it 91? 6? Did I get that right? 91, you got that too? Sierra, what did you get in there? 91, okay. So 91/6, which is, let's see, 6 goes into 91. That's going to be, I think that's right. 15 1/6. Okay, so we're almost there. We can now calculate our variance. What's this? That's the 91/6. Yeah, I'll keep it as a fraction, maybe easier here. And then what's this? What's that? That's the 21/6. And I have to square it. Okay, so somebody help me out. What's that? 2.91. Others get the same? Seeing some heads nod. Okay. Can I get a couple more decimal places? Okay, 6, 7. Okay, that's our variance. How do you think we find our standard deviation? Square root, right? Yeah. So let's take the square root of this. And what does that give us? I'm guessing it's going to be 1.7 something. .7078. Do we agree? Nice. Okay. So we had this tool called the expected value or the average of a probability distribution, which helped us to find the center part of it, which helped us with decision theory, making decisions about bonds and about different games of chance. And we also have the standard deviation that we can calculate, which describes how much dispersion there is in this distribution as well. Oh, sorry. Okay. Okay. Box contains 5 balls. 2 are numbered 3, 1 is numbered 4, and 2 are numbered 5. I love these things. It's like, who cares? The balls are mixed and 1 is selected at random. After a ball is selected, its number is recorded. Then it's replaced. If the experiment is repeated many times, find the mean, variance, and standard deviation of the numbers on the balls. So, how many balls do we have totally? 5. 2 are numbered 3. So what's the probability of pulling out a 3? 2/5. Okay, good. 1 is numbered 4. So what's the probability of pulling out a 4? 1/5. Still 5 total. And then lastly, 2 are numbered 5. And so back to 2/5 again. Okay, very good. This is X. This is P of X. Calculate that, and calculate that. Just use the first of your two equations that you'll want to see to it go into your test taking resource. Here's the second of the two equations here. People tend to forget this second part over here. All right, x squared 3, 4, 5 becomes 9, 16, and 25. And if I multiply each one of these by p of x, you get 18 25ths, 16 25ths, no, 16, 18 fifths, right? 18 fifths, 16 fifths, and then 50 fifths. So that's going to be 68 plus 16. So it's 84 fifths, I think. And so variance here is going to be 84 fifths minus 4 squared. And 4 squared is 16, which is 80 fifths. So 84 fifths minus 80 fifths. Oh, that's just 4 fifths. So I can get this by taking the square root of 4 fifths. It's going to be the square root of 0.8. And I don't know what that is. Sounds right to me. Do we
Yeah.
agree? Good. Okay, so we've calculated the mean, the variance, and the standard deviations. Big equations to remember here for this section are these two. And then also remember this stuff here, how you calculate this stuff. Ready? So yeah, we'll skip this. Just practice the same thing here. All right, very good. So one last thing I want to show you is something called the binomial distribution. And when project 4 is done, you'll have some time to, your next project will involve creating something that does this for you. But the binomial distribution allows us to, come on, be nice, allows us to ask questions like this. Lionel Messi is an Argentinian soccer football player. Out of all his attempts on goal, he actually makes a goal 60.32% of the time. That's real. If he has 3 goal attempts in a game, what is the probability that he will make none of them? Is that a possibility? Yeah, he'll miss every single one. Is it a possibility that he'll get goals all 3 times? That's a possibility. How about if he gets exactly one of them, exactly 2 of them? Those are probabilities as well here. We can find that out through the binomial distribution. So again, we've got a binomial experiment here, heads or tails, test question true or false, test question response correct or incorrect. This gets into the thing with Kavanaugh that we were doing earlier today. So fixed number of trials, only 2 outcomes, one we call success, one we call failure. The outcomes of each trial must be independent of each other, and the probability of success must remain the same for each one of these. So Are these binomial experiments, each one of these? Take a look at these four criteria here. Fixed number of trials, only two possible outcomes, independence, probability doesn't change. Selecting 20 university students and recording their class rank. Binomial experiment or not? No, why not? It's not binary, right? It's not one or the other. The class rank can have a bunch of different values. Okay, so it's not a binomial experiment. Selecting 20 students from a university and recording their gender. We're assuming binary definition of gender, and we will say, yes, yes, that's a binomial experiment. Drawing 5 cards from a deck without replacement and recording whether they are red or black cards. Yeah, that's a binomial experiment. Selecting 5 students from a large school and asking them if they are on the dean's list. Yeah. Recording the number of children in 50 randomly selected families. How many possibilities are there for an answer? Not just 2. You could have 0, 1, 2, 3, 7, 14. Who knows how many kids they've got in the family there. So, all right, cool. Oh, without replacement. 5 cards from a deck without replacement. Does the probability stay the same when you pull out your first black card or your first red card? Those things change. So, all righty. So the outcomes here, we say, have answers that are distributed as a binomial distribution. Okay, so in other words, the shape of the distribution, the probability distribution, is going to have this kind of shape. It's a binomial distribution with this number of trials and with this probability of success. You're going to be creating something that actually creates this stuff for you in your own spreadsheet. By the way, how are we coming with project 3 here? Some stuff here. Okay. Oops, that's not what I was wanting to look at. That's the workbook I'm working on. Okay. But here's what project 4 is going to involve. You're going to be putting in different values here of n and p, and it's going to be creating this binomial distribution here for you. So 15 trials, 50-50 chance of success. So in other words, you're flipping a coin 15 times. About how many heads or tails would you expect to get? About half and half, right? You have this probability of getting 7 heads, this probability of getting 6 heads, this probability of getting 5 heads, 4, 3, 2. Is it a possibility of getting no heads? Yeah. Possibility of getting all 15 heads? It's like this. Let's make it 25. Okay. So it's still centered, in this case, 12 or 13. Things drop off a little more quickly. I think, and I designed this so that you can go up to 50, but not any higher than that. So you can see here, yeah, these probabilities are really, really small, and you can actually see them listed up here. Tiny, 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 tiny. Okay. And what if I'm taking a look at rolling a single die? Okay. The probability of a number of 6s if you roll 50 dice. It's going to be about a 6th of them, about 6 to 10 of them. Okay. There's a possibility you'll get 56s. It's very unlikely, but possible. But yeah, and you've got mean, variance, standard deviation being calculated here as well as percentiles for each one of these. Okay, and this is the actual distribution here. The regular distribution and the cumulative distribution, that's plotted here. Okay. You'll actually do the same thing for a normal distribution. You'll be able to plot multiple normal distributions. And we'll also eventually create this thing here. We'll actually probably do this in class. Okay, so this is what the equation actually looks like for how it's calculating that. So, This is the part where we thank our lucky stars that we have a spreadsheet calculating this for us. Okay. Yes.
Would we be able to use the spreadsheet on the test?
Yes. Yes. So, yeah. And so you can see an example here. A coin is tossed 3 times. Find the probability of getting exactly 2 heads. We should get this from our previous experiment here. And yeah, if we plug this into our equation here, yep, we get the right answer. Okay. A survey found that 1 out of 5 Americans says he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. Well, plugging it into this formula here, and you can find out that the answer is 20.1% here. Or you can put this into your spreadsheet. Be nice. Into your spreadsheet. And how many people are asked? What was it?
Was it 10?
I don't remember. 10 people are selected at random, and what's the probability that they've visited a doctor? 1 out of 5. Okay. So 10 people. And 1 out of 5 is 0.2. So what's the probability that 4 of them? Well, there it is.
3.
Oh, 3? Okay. So that's 20.1% right in here. That's this. Okay. So you just read it off of there. We can use this. I don't know why my computer is suddenly about to die. That's probably the reason. In fact, I should probably plug this in here. Okay. So coin is cost 4 times. Find the mean, variance, and standard deviation of the number of heads that will be obtained. You've already come up with this here. What's cool about these probability distributions, if you know it's a binomial, the equations for mean, variance, and standard deviation become a lot easier. Look up above me. The equation for the mean is just n times p. Variance is just n times p times 1 minus p. And then you just take the square root of that to find the standard deviation. So that has been known to pop up on a test where I give this to some students and I tell them that it's a binomial distribution and they're like, oh, probability distribution, sum of x squared, 3x. No, you can just, Okay. So here's an example. Let's come back to this here. Lionel Messi is an Argentinian soccer player. Of all his attempts on goal, he actually makes a goal this percent of the time. What's his probability that he will make none of them, exactly one of them, 2 of them, or all of them if he has 3 goal attempts? So what's n for this? How many attempts does he have? 3. So it's 3 trials. Each time he does it, what's the probability that it goes in? 60%. Okay. So there's a possibility he'll make none of them. There's a possibility he'll make all of them or 1 or 2. Well, we can calculate that using our spreadsheet here. So 3 attempts at 0.6032. These are our probabilities. So if we zoom in here, what's the most likely scenario? Most likely scenario? It's not.
That's 0.00.
Oh,
0.0.
It makes 2 out of 3. That 0.433, that's the largest probability there of all of them, isn't it? Yeah. Yeah. Does that seem about right? 2 out of 3 times? 60%? Is that right? Yeah, that makes sense. So, by the way, what do all these probabilities add up to again? 1? Yeah. Do you think this is helpful for people who bet on sports? So people spend all their time doing this kind of stuff. So they're looking at this kind of stuff here quite a bit. You know, if a batter, you know, for the Colorado Rockies, poor Colorado Rockies this year, you know, has a batting average of 0.3, that means they get a hit about 30% of the time. And so if they're up to bat 5 times in a game, then they'll probably make about, you know, 1 or 2 hits.
They're like, they're not hitting any.
It's like, so you can describe, you know, those probabilities as well here. Okay, so you know, and there are other types of problems that we can do with this here. Tina Charles is a WNBA player for the Seattle Storm. Her regular season free throw percentage for 2022 is 88.5%. If she has 6 free throw opportunities in a game, what's the probability that she will make exactly 4 of them? We can calculate that with the same thing here. Now, Brendan Rodgers is an MLB player for the Colorado Rockies. His lifetime batting average is .266. If he's at bat 4 times, what's the probability he will achieve a hit exactly 2 times? Now, remember, these are binomial experiments, and just like we did with Kavanaugh, we can deconstruct this stuff a little bit. Remember, there's some things that we're really assuming here. Fixed number of trials, that's fine. Independence is probably the big thing. If I'm up to bat 3 times and I strike out 3 times, how confident am I the 4th time I go up? So you might say my chances of getting a hit might be a little less this time here. So this assumes none of that. This assumes every single time they walk up, it's a new day, you know, they're giving it another try, as they always do. And there's no psychological factors at play. So okay, we can also apply this to hockey here. Cale Makar is an NHL player for the Colorado Avalanche. His lifetime shooting percentage is 10%. If he has 7 shots on goal in a game, what's the probability he'll make exactly 5 of them? Probably not very likely, but you know, we can calculate what that probability is there. Okay. So we might spend a little more time on this next time here, but this is the last part of chapter 4. We have done all of chapter 4 in essentially one day here. I am curious as to whether or not we can talk a little bit more about Project 3.
On Thursday.
Yeah, it's on Thursday. I knew there was something that was kind of weird.
What kinds of stuff have you done? Somebody's doing this? Okay, all right. Not much. So, probably the best thing to do tonight is to take a look at your data and construct that 5-member summary for not only the first data set, but the other 2. And then also at least take note of what the average is, standard deviation, and the also the box plot and a histogram, what it looks like. That'll give you an initial look at the data. We'll also do scatter plots for each one of those things. See if you can build what the story is. So just take a look. So just take the time to create those things. You just paste them into your Google Doc that you're putting together. And once you've got all those things created, you've already gained a large number of points towards the completion of those. The big thing then becomes, what does this mean? 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 And just if you're building your story, what it looks like. But probably the big thing today is just get those charts finished, paste it into your doc. And you'll want to get that done probably to get that. The thing I don't want to happen to you is, it's Thursday night and it's 11:30, you're panicky. I just don't want that to happen to you, as it's happened with tons of previous students. Yeah. Do we want to spend a little time just opening up and taking a look at it, asking questions? Okay. Well, yeah, right, because you're still in the data sheet. You want to copy all the stuff into your spreadsheet. Then you'll be able to do that. Yeah, I make it so that people can't mess with the raw data here. So you are right. Yeah. That sounds good. Yeah. Yeah, project 3 data. Okay. I don't feel the need to keep you here. Done. But you did an awful lot today. We did a little bit of additional work with probability with the Kavanaugh problem. We started this concept of probability distributions. We defined what they were. We defined what a random variable was. We started to describe how you calculate statistics, probability distributions, and how you can use those statistics to choose between different investment options or different games of chance to engage in. And then lastly, we ended up with a good introduction to the binomial distribution. The big day. Big day. So pat yourself on the back with a lot of stuff.
You're kind of ill, sir. I'm just a broken person.
Oh, I do. I can hand back your tests. I keep forgetting to do that. Wow. Oh well.